We're going to jump in here about estimating a population proportion. Okay, so what we're doing this time is trying to use a point estimate to estimate the population proportion. A point estimate is a value that we generally get from some sort of a sample or a previous study, and we use this to give us an initial estimation for a population parameter. So the sample proportion is referenced as p hat. This little p with that arrow over the top of it is really called p hat. I'm not making that up. And it's the best point estimate of the population proportion. Now we use p hat as a point estimate for p because it's unbiased. And it's the most consistent of the estimators that could be used. So now that little red asterisk there beside unbiased, an unbiased estimator is a statistic. So again, this is estimators coming from some sort of a sample, and it targets the value of the population parameter because the distribution of the statistic has a mean that's equal to the corresponding population parameter. Now you don't have to so much understand that. We wish you did, but if you don't, you do need to make a note that the point estimate p hat is an unbiased estimate of p. Okay, if we took a lot of samples and we found the proportion from all of the samples, and then we took the mean of all of those sample proportions, that mean would actually be equivalent to just taking the proportion of the population. So that's a little bit overwhelming. I understand it often is, but make sure you make a note that this is unbiased. So we use p hat as the point estimate for p. Just a very brief example, a Gallup poll is taken, 1,487 adults were surveyed, and 43% of them said that they have a Facebook page. Based on this result, what is the best point estimate of the proportion of all adults who have a Facebook page? Well, since we have a previous survey that says 43% of them, 43% from this previous study would be the p hat, and p hat is the best point estimate for the population of all the adults, so 0.43 would be our point estimate. So you take the information from a previous study, and then you say, okay, then we're going to estimate this is in fact representative of the entire population. We're not saying it's perfect, but it's the best point estimate. Moving on from that, we then take our point estimates and we create confidence intervals along with confidence levels. Now those terms sound very similar, but they're not the same thing. Okay, a confidence interval can't really be created unless you know the confidence level. In other words, you have to decide how sure you want to be before you create the interval that goes along with that. So an interval, and sometimes it's called an interval estimate, but we will consistently call it a confidence interval. A confidence interval is a range, or we might call that an interval, of all the values used to estimate the true value of the population parameter. So it'll have a beginning number and an ending number, and we'll say that the population parameter is somewhere in between those. Now, our confidence level is really how sure we are that that interval actually does contain the population parameter. So if I had 100 teams and I wanted to tell you, oh, I could tell you which teams are going to make it in the playoff. If I only list 2 teams, I'm not really very confident. But if out of 100 teams, if I start to list 80 of them, I'm going to be really confident. So what happens is that we have to include more in the interval to be more confident. So if we have a very small interval, we're also going to have a smaller confidence level. And if we have a larger interval, we will have a stronger or higher confidence level. Now, it does assume that this estimation process is repeated a large number of times. So this is actually referencing a process. The confidence level is sometimes called the degree of confidence or the confidence coefficient, but we'll be calling it the confidence level throughout this text. how do these relate? There is a little note alpha that we will use, and an alpha is related always to the confidence level. Let me back up just a minute. I kind of glazed over this. Do you see here where it says confidence level is the probability, 1 minus alpha? So if we were 95% confident, then my alpha would have been 5% or 0.05. So you could always calculate that out, but you can see then this connection. These are the most common confidence levels we use, and then they have a corresponding value of alpha, which right now I'm sure you don't see the importance of, but we'll sometimes need this number, okay? So 90% confidence level means the remainder of my probability is 10%, and that is my alpha, 0.10. 95% confident, the remainder of probability is 5%, so alpha is 0.05. So you can see the connection between those. And these are the three that we will use most often, 90, 95, and 99. And their corresponding alphas are 10, 5, and 1. 95% is the one we use the most often, though. So 95% and that alpha of 0.05. So right now, before we do anything else, let's just talk about how to interpret a confidence interval. Because there's some wrong ways to do it. I have two wrong ones in here, small, and then I have a large one that's correct. So suppose your homework tells you to interpret a 95% confidence level of the confidence interval that P lies between 0.405 and 0.455. Okay, well remember, this 95% confidence level is how sure we are that the actual value is in the interval. So the correct thing to say is we are 95% confident that the interval from 0.405 to 0.455 actually does contain the true value of the population proportion P. Now you could rephrase that, but not a whole lot. Like you could say we're 95% confident that the true population proportion P lies within the interval. So we're just saying that we're 95% confident that it really is in there. So don't be misled by other ways to re-say it. I don't even want to say these aloud. These are not correct ways to kind of deal with that, but you're going to have to do some multiple choice on there. So always just say that you're 95% confident. It is relating to your confidence that it's in there, not the possibility that it's in there, but the confidence that it's in there. Okay? Confidence interval is how confident you are. And I have a little note here. That's because it's about your process working. The method is about, are you sure you did it right? Well, I'm 95% sure that this will hold it. Okay? Critical values are the numbers that, if you're looking at your distribution, the critical values are z-scores. And z-scores, they're the critical values that separate what is considered high or low. And they are related to alpha. And don't forget, alpha is related directly to your confidence interval. Even though it's not official, I'm going to put CL. Okay? CI would be confidence interval. But if we have a confidence level of 95%, then that tells me that alpha would be 0.05, representing that other 5%. But if that is the case, then alpha over 2 would be half of that. And that would be the area that is in one tail. Now, I'm going to talk some about other slides about how to find the z-scores that go along with that. But it's important that you know the area that's in the tail. Now, that area is in both tails, both on the bottom and the upper. But when we're looking at a critical value, notice that the critical value over here is positive. There is a negative one also, but initially they often just ask you about the positive one, and then we know it's plus or minus because this is a balanced thing. Now, of course, that does mean that if my confidence level was 99%, for example, Then my alpha would be, I can't really draw that on there, alpha would be 0.01, and then alpha over 2 would be 0.005. And so that would represent the area over there. And there was one other one that was common. It wasn't as common as the 95, so I did that one first. But the other confidence level is that if we were at 90%, then the alpha is at 10% or 0.10. So alpha over 2 would be 0.05. It's going to be important that you know how much that alpha is, but also the alpha over 2, so that we can get this z sub alpha over 2. And you can see a little note here that we're going to be able to find that on your calculator. Okay, so here's how to find that on the calculator. Now, if your calculator doesn't have a center option, and I've done this with the 95%, but if your calculator doesn't have a center option, you would have to use a cumulative area coming from the left of 0.9750. And so again, just to kind of help you see that based on what we had on that previous slide, if we have 95% in the middle, which is where our confidence interval is going to be, then we have 5% left over to put in each one of these parts. So if I take that 5% and I split it between those two tails, then this is half of 5%. Now, if you have a calculator that won't let you do the center section, then your calculator comes from the left. And so you're needing to put in all of this area. And that's why that we have this 9750. It's because coming from the left, the 0.025 plus that 0.95 is that value, 0.9750. Now, I did inverse norm. I don't have up here how to get to that because we've done it before, but I'll show you again real quickly. So all of your distributions are found underneath second vars, and the same is true for the inverse of those. So it goes second vars, and then you don't see it, you might not see all of the inverses you need, but inverse norm is right here, number 3. And so this that you're seeing right here is exactly the screenshot that I copied and pasted. So since it's a z-score, we do leave mu at 0 and sigma at 1. Z-scores are always the standard normal, so leave it 0 and 1. And then my area was 0.95. Now this should not have been what was here. I meant to copy and paste the results. So let me bring them back up and show you the results since I didn't get it copied and pasted correctly. So since mine goes from the center, if you have this option, you can just put it in the center and put your confidence level right there. And I paste. And there's my result. And I get this negative 1.9, and we're going to call that 6. So negative 1.96 to positive 1.96. That's actually not an interval. Those are my z-scores. Okay, that would mean that these values right here were negative 1.96 and positive 1.96. So let me just kind of put that here. This should not have been here. What you should have had is something that had negative 1.96 and positive 1.96. Now, again, if your calculator only comes from the left, you're only going to get one of these values. But they're the same, and they always will be. It's just that one's positive and one's negative. So you're always going to have plus or minus your z sub alpha over 2. And if you're online and it asks you for alpha over 2, it only wants the positive one. Okay, we know the negative one is involved as a critical value. But see how this says find the critical value, z sub alpha over 2? It is 1.96. And that would be the answer. The other one is the negative z sub alpha over 2. If they don't put that negative in front, they're wanting the positive one. Now, there are some that come up a lot. So here's another just kind of summary. I definitely write these things down. This is going to save you some time so you won't have to do it over and over and over, since these are the three most common confidence intervals and then the corresponding alphas. Every single time you put a confidence level of 95% in the calculator, then it's going to give you that 1.96. Well, similarly, you could do it with a 90% confidence level or 99, and you will always get these values. So making a little note of them somewhere is faster than redoing it, and I would recommend you do that. Now, we're going to be using the 1.96 the most because most of our problems deal with the 95%. Now, margin of error is another concept going along, and so this has to do with knowing that once we make an interval for our confidence interval, we recognize we might be off, and so we can have an error. And that margin of error we abbreviate. Now, this abbreviation certainly makes sense. It's a capital E. And there's also, you see this 1 minus alpha again. So if we're dealing with 95%, we would say that there's a 95% probability, or 0.95 probability, that the difference between our estimate, p hat, and the population proportion, p, is E or less. So we're looking at saying we're 95% that we're not off by more than that. 95% probability we're not off by more than that. Now, this E is also called the maximum error of the estimate. That's because it's E or less. So E is the maximum error. It's important to get that terminology, though, because if they ask you for the margin of error or the maximum error of the estimate, it's E. Now, there's a couple of ways we can go about finding it. If you need to use a formula, which is coming up on the next slide, it is found by taking the critical value, like the 1.96, and you multiply it to the estimated standard deviation of the sample proportions. Okay, so what does that look like in a formula? It's right here. We have just found out, like for a 95% confidence, our z sub alpha over 2 would be 1.96. And then this part over here, all of this, including that square root, that is the estimated standard deviation of sample proportions. So p hat, like if we said 43% of adults had the Facebook, then 1 minus 43%, which would be 57% of them don't. So we would have 0.43 times 0.57 divided by, I can't remember right now, the 1,047 or however many people were included in the survey. Okay, it would take the square root of that and multiply it by that. So you might need that formula. However, a lot of times we're going to be able to use a different approach with the calculator. You're most likely to need that formula if they simply just give you this information and ask you to calculate it directly. So we can do a direct calculation, because if they tell me how confident I am, then I can get the associated z-score. And if they give me background information about a previous study, I can identify my p hat, and then 1 minus my p hat is q hat. N is the number that's in the study. Okay. However, I really don't use that formula unless it's the only option I have. So we're going to look at another way to go about it in just a minute. The confidence interval, if you are going to estimate a population proportion P, there are requirements. Again, this is important information because some of your homework will simply give you some sort of a word problem and then ask you if the requirements are met. So what are the requirements? The sample needs to be a simple random sample. That's the first one. Second, the conditions for the binomial distribution need to be satisfied. So what was that? That was a few lessons ago, so we just kind of got that in summary here. There has to be a fixed number of trials. The trials have to be independent. There's only 2 categories of outcomes, like success and failure, and the probabilities for those are going to stay the same for every trial. So it is a simple random sample. It is a binomial distribution, which includes all those things. And there are at least 5 successes and at least 5 failures. Okay? Once we've met all of this, then we can come up with the confidence interval. So we have to meet all of those for this to apply. And the confidence interval can be expressed in a couple of different formats. We can either take our p hat plus or minus e, or we can put it in parentheses. And this is an interval notation, but we can also just change this interval notation to say that p is between p hat minus e and p hat plus e. So we'll do a little bit of rearranging and then work one of these problems out completely here. But when you do a confidence interval limit for p, we're going to 3 significant digits. All right, so first of all, let's just look at the different forms we can have it without having to worry about how to get it completely. If you have it written like the actual p is between these two values, then we can rearrange it. Notice the difference between p is between these two values and this one down here where it's just written in parentheses. I don't have any practice for us to do that because that is just almost direct. We could take this one and put parentheses 0.0434, comma, 0.217, close parentheses. It'd be the same sort of a thing. So we don't practice that, but we are practicing taking these formats into the 2 other formats. Well, first of all, it kind of helps to understand that doing p plus or minus e, if you consider a number line, if you add e, you get to a bigger number. And of course, if we subtract e, we get to a smaller number. What these numbers are telling us then is that these are the numbers we get to. So between this smaller number, 0.0434, and the higher number, 0.217, we could take that distance and cut it in half, and we'd get to p. So how do you take the distance and cut it in half? And there's kind of 2 things to do here. One of them is that we can take the high value minus the low value, and I'm just kind of abbreviating there, and divide it by 2. The high value minus the low value will give me that distance. And then when I divide that by 2, I will actually know what E is. On the other hand, if I'm trying to find P from those 2 numbers, to get in the middle of 2 numbers, I add them and divide by 2, P. So I'm going to bring up the calculator and let's just do that. So first of all, if I'm going to find P first because it says P hat, and that's really what this should have been marked. I'll go back and add that in a minute, P hat. But what we're going to do is we will add them and divide by 2 to get to that middle number. So I have 0.0434 plus 0.217. And since I didn't enter it like a fraction this time, and I could have, but I just didn't, I'm going to add them and then divide by 2. All right, so that gives me the number in between those 2 endpoints is 0.1302. 0.1302. That is actually the P hat. And again, this should have said P hat. So P hat is what I'm dealing with. And again, that was 0.1302. Now, plus or minus E. So to calculate E, I want to know the distance between those 2 numbers and then divide it in half. And again, this time I could have done it before. I'll hit alpha y equals and put it like a fraction. It doesn't matter how you do that, but I want to take that upper number. And I think I did the lower number here plus the upper, but when you're adding it doesn't matter. When you're subtracting it does. So I need to take the higher number minus that lower bound and then divide it by 2. So again, you can do it in pieces or we can do it all at once. But when I subtract and divide by 2, that tells me half the distance. So this one is my 0.0868, 0.0868. That's what I got when I just did those. I am going to back up slightly to something else. Notice it says round the confidence interval limits to 3 significant digits. These values, the limits, were at 3 significant digits, okay? You don't count zeros that are just holding the decimal away. And so this is 434. And so this one also has 3. So I know they don't have the same number of decimal places, but decimal places and significant digits are different. Now down here, this one is not rounded. Once you do your intervals, notice all these intervals are going to have 3 significant digits. So this one is the answer to that very first way. In other words, we could say our p hat was 0.1302, and then the error was 0.0868. Another way then, if we have this, I could have practiced this writing the interval, but if you have it this way, it's not hard to get it. Because once you do the subtraction, if you take these two numbers and subtract them, you'll get your lower end. And if you take the two numbers and add them, you get the upper end. So going directly is not quite as difficult as going backwards. So we're going to do this again, but we're just going to write it differently. So when I go to here, I'm going to say that my actual proportion is between those two values. So it might want me to do this. And then this. Now my P is in between those two values. Now if I do need to identify my specific P hat and error E, again, I'm going to go back down here and do this. So if I take the nice thing about doing it all at once like that is because then I can go up and copy, and then I can simply go back and change that plus into a minus without having to retype it all. So once with addition and once with subtraction. So if that's it, then my addition, again, is finding my P hat. So that one is the 0.07995. And then my error is the 0.06305. So I have found and identified them specifically if I need them. In neither one of these did we use that formula, but again, the formula is really if you are starting with the information from the previous study and you're trying to find that. That's what is kind of summarized here, and then we're going to work through a problem completely. We have to make sure that we have verified the requirements. Then we're going to find a critical value. That's our z sub alpha over 2. Then we can find the margin of error. Now, notice here it says you may need this formula if your problem directly asks for the margin of error. We're actually going to be able to even bypass this because we can use our calculator to actually calculate this confidence interval. So this time I'm going to try to do it both ways for us, and we will get that confidence interval calculated. So that's our procedure. So going through, this is what a homework problem can look like. And this is back to that same example I used earlier. A Gallup poll of 1,487 adults showed that 43% of the respondents had Facebook pages. So the sample results were N was 1,487 and P hat was 0.43. So right here, I'm going to start off by using that formula for the margin of error. Because it says 95%, what 95% tells me is that my z sub alpha over 2 is 1.96. Again, I could get that from my calculator, but that's the same one we calculated earlier. So the formula I'm about to apply is this one, where I take that 1.96 times the square root of p hat q hat over n. So my error is equal to 1.96 times the square root of p hat. That is, we looked at that one earlier, that's the 0.43. And then q hat is 1 minus that, and you can put that directly into a calculator if you don't want to do the subtraction and take a chance on subtracting wrong. I think that's 50.57, but I'm just going to put 0.43. And then we're going to divide all of that by n, and n was 1487. I'm going to bring up my calculator and put all that in at once. So first of all, 1.96, and then the square root, which is second x squared. Then within the square root, I'm going to put a fraction, and that will be 0.43, and then 1 minus that value, over n. And I get this long decimal, okay? We're going to go 0.0252. 0.0252. And we're going to compare that to doing this another way in just a minute. Okay, so now find the 95% confidence interval estimate of the proportion. Well, what we know is that we're going to take our p hat plus or minus e. So p hat was right here, that's the 0.043. So I really have 0.043 plus or minus 0.0252. Now there's two ways to write that confidence interval estimate. I'm going to put it here in parentheses. So we'll go back 0. And that should not have been 043. I don't know why I wrote that down like that. 43 plus 0.0252. And then I can go back and I can copy and paste again. I love to do that, so I have to type it again. Just change my plus to a minus. And of course, the minus one's going to give you the smaller value. So 0.4048, 0.4048, and 4552. I'm going to make that correction here. That's not where that went. It went 0.43 right there. So that's how I have found then my confidence interval. Now, my confidence interval is not exactly right now because these numbers have 4 significant digits. And I was told to round it to 3 significant digits. So even though I wrote down the 4, now I'm going to make it go to 3. And I don't want to round to rounding, so I better look at my calculator again. So to 3 significant digits, that would have been 0.405, and this one would have been 0.455. So 0.405 and then 0.455. That would be my confidence interval. Now, on the next page, we're going to go a little bit further. So notice this is part A and part B. We've got part C and D on the next slide. I didn't want to put it all on one slide, but we're still working with this same problem. So part C, or maybe there's only part C. Based on the results, can you safely conclude that fewer than 50% of adults have Facebook pages? Now remember, the survey said it was 43% in their survey. So could we conclude that there were fewer than 50% of adults with Facebook pages? This being 43%, what we're really going back and looking at that confidence interval is we are 95% confident that the true proportion lies between these numbers. Since we are 95% confident and both of these numbers is less than 50, then I would say yes, we can safely conclude. Now, assuming you're a newspaper reporter, write a brief statement that accurately describes the results and includes all of the relevant information. So certainly when you're doing this online, it would be a multiple choice thing, but what you're looking for are some of those key phrases. 95% confident, that's going to be a key phrase somewhere in what you need to say. And that we're not saying there's a 95% chance or anything. We are 95% confident that the true proportion is between, and that's where we put our confidence interval. We could also use a little bit more information on there. That error is how far off we may be, and so that's approximately 2.5%. We don't expect our proportion to be off more than 2.5%. So there's a couple of different ways we could say that. Let's look at what would have happened if we wanted to use our calculator. Yay for these calculators for this. Same problem. I could go into stat and test. Now that's not where we've been before. So bringing back up the calculator, stat, test. I'm going to make it big for you for just a minute here. We have been using things under second vars, which is a distribution. But if you go to stat, now we've used this before back when we entered a list, but we did not go over to test. So go over to test. So stat test, and then notice it says choose the one prop Z test. This means you have one proportion, and we are looking at a Z interval. That's given us our critical values between two Z-scores. Let me minimize this for a minute then. What I did when I went to that one prop Z interval, I chose interval, even though it's underneath a test. Don't get confused. There are several things listed underneath this option, and I know that there's lots of tests, and I even see here this one prop Z test, but notice that is not what we picked. This is the one prop Z interval because I'm trying to find an interval. So it's not here on my very first screen. You can either scroll up or down to get to it, but it's going to be here. It's at option A, so it's about as far away from the first screen as you can get there. And option A says one prop Z interval. So it's found under a test, but yet you are creating an interval. Biggest tip I can give you on the calculator there. Okay, then I was able to put in my information directly from the problem. Now I say that, but yet the number 639 was not given to me in the problem. However, it did say 43 of the respondents had Facebook pages. So I can find 43% of 1,487. And that number is 639. But suppose I didn't find that ahead of time. You can just say, well, it is 43% of 1,000, and how many was it? 1,487. So right there, you don't actually have to know ahead of time what your X value is. You can just put that in, but I recommend that you go ahead and find it out because, for example, if you multiply on something like this, you could get a part of a person, but we know that we did not have a part of the person respond. You had to have an entire person respond. So this is how I did it, but I just did it on that other screen, okay? 0.43 times 1,487. And notice this does come out to that part of a person, but I rounded it off to a whole number to say 639 people. Okay, and that rounding can make a difference. So since it's people, we need to go with a whole number, and it should be a whole number since it was binomial. Then after you put in then that X and the N in the confidence interval and click calculate, the result it gives you, this is our confidence interval. Now let's go back and compare that to what we had earlier, 0.40456. 0.40, and see, I've rounded it, but that 4045 is what rounded right here. Now my other end was 0.455. So let's look at this one. This rounds to 0.455. So this number it's given you is not rounded to the 3 significant digits, but it is the right value. Now, if we needed to know E for a problem, we can use our previous approach. Once we have our rounded interval, half of that interval length is your error. So the error ended up being 0.25. So now let's go back and compare that to using the formula. Here was our formula, and we do get 0.025. 0.025. Did I say 0.25 on the other one? Yeah, this should be 0.025. Another mistake there, but we cannot afford to start this video over. So that should be 0.025. Okay, have the decimal in the wrong place there because those fours should be the same. So we got the same error also. And then it tells you the p-hat, so you could verify that. Yeah, that does come out to 43%, just like my problem told me. But you can get this then in most of your stuff just by using this confidence interval that's on your calculator. Stats, test, and then option A, which even though it's under test, make sure you don't pick the one that says test. It ends with INT for interval. All right, now just a few more slides. We've done the main part of it here. When you analyze the results from polls, make sure that you consider other things. The sample needs to be a simple random sample. If they don't do a simple random sample, the poll really doesn't mean much. That's why all these internet polls and surveys, I mean, who cares? It means nothing. They should also tell you the confidence level, because the confidence level changes the length of the confidence interval. A stronger confidence level, like 99%, is going to have a bigger interval because you have to go, actually, your interval has to be less precise so that you can be more certain you've got your stuff in there. The sample size should be provided. Now, there's just a little note here. Normally, what's wrong with a poll result is the sampling method or the size of the sample. The size of the population is not normally a factor, and that's important to keep in mind. You might think, well, the population is huge. How can this be right? But it has to do with more, did they do the sampling correctly, and did they use a large enough sample size? So sample size is important. I've already done this. I actually did this earlier when I said p-hat, you can add and divide by 2, and then on the margin of error, you can subtract and divide by 2, so we've already covered that. But I think we've got something coming up about sample size in a minute. So let's just look at this one, finding the sample proportion and a margin of error. It's just another example. We've got a statement of the 71 subjects, 70% were abstinent from smoking at 8 weeks. Okay, now that 70% is going to be our point estimate p-hat. So p-hat is 0.70. Now find the margin of error. It says the confidence interval is 58% to 81%. So let me just kind of change that to the decimal. 58% to 81%. Now this one's going to come off like to a 0.5 and have to round, but I'm going to bring up the calculator and we'll do that again. So if we take alpha y equals and we add, divide by 2, and then we're going to back up and I'm going to change that to subtract and divide by 2. So you can see this 0.695 is approximately the 70%. I think because it tells us directly it's 70%, then we would use that as our p hat. But then our error is 0.115, so that is my E. If you have a problem like this on your homework, I really recommend you click Show Me an Example, because there's 2 appropriate ways to do it. You can either use the addition and subtraction method, which I'm going to change that number there. Oh, that was 0.695. So if I use this addition and subtraction method, I get 0.695, and then it's plus or minus my error over here. And if we did that, that should work. The other thing we could do is we could use the formula. And so if I were going to do E, since it says 95%, I have 1.96 times the square root of 0.70 times 1 minus that, which is 0.30, divided by my 71. So let's see how close that one comes out on the calculator. And so that error comes out to approximately 0.107. So as you can see, these are not coming out identical. Now they're awfully close, but they're not the same. Which one should you use? They're actually both correct, and that's real annoying. So we could use 70% as given and then use the formula, or we could use the addition and subtraction. Which one should you use? There's no way around it, guys. You're just going to have to click Show Me an Example and click through it pretty quickly to just see, did they use the formula or did they use addition and subtraction? They're both appropriate and they're not going to be quite the same. But if you notice that if you take 0.70 plus 0.107, you end up with 0.807, which rounds to 81%. On the other hand, if you add them here, you're going to get 0.695 plus 0.115, and that ends up being 0.81 exactly. So they both work. Which one should you use? I wish there were a great answer for you. I would be doing the same thing you are. How big of a sample should you use? I did say the most important problem is typically not the population size, but either they didn't take a simple random sample or they did not have enough included in their sample. So simple random sample has to do with sampling method, but how do you know how many you should include in your sample? Well, there's a formula for it, okay? If you have any sort of an estimate for p hat, then you use p hat and q hat right here. Now, if you don't have an estimate for p hat, you assume actually that the probability of each one of those is 1/2, but then 1/2 times 1/2 is 1/4, okay? So that is where this 0.25 comes from. It comes from saying it either is going to happen or it isn't, and if we have no idea, then we use a 0.5 for both of those, okay? Now, whenever we use these formulas, if you don't get a whole number, you have to round up, not round really. Let's just say go up. If it's not a whole number, go up, because you have to make sure you have a sufficient size, not just close. You might need a little bit extra. So these formulas have our Z critical number here, alpha over 2. So you'll take that critical number like the 1.96 and you square it. You have to pre-decide how much of an error you're willing to include. Like, I don't want to be more than 3% off. Well, that would be your error. Or I want to be within 2% of, okay, well then 2% would be your error. So you have to decide how much of an error you're willing to tolerate, or that has to be provided for you in the question. And then it is a matter of using those formulas, and you will need those formulas. So let's look at this. You need to conduct a survey to determine the percentage of adults that make online purchases. How many adults must be surveyed in order to be 95% confident? Okay, the moment we see this 95% confident, that's important, because what that is actually telling me, I can't even draw a straight line on here, but what that 95% confident tells me is my z sub alpha over 2. Z sub alpha over 2 that goes with 95% is 0.196. But then it also says that I want to be 95% confident that my error is no more than 3 percentage points. So what that is telling me is that the E is 0.03. In part A, we can assume that we have a survey that showed that 80% of the adults make online purchases. That means we have a p-hat of 0.80. So we're going to take this information and the formula. I'm going to go back to that formula page, but we know p-hat is 0.80. My z-score is 1.96, my critical value z, and then my error is 3%, and we're going to calculate that on the formula. So first of all, I guess back to the formula. I do have an estimate for p-hat, so I'm using this first one. And I know that I'm covering up n equals, but what happens is I have, first of all, I'm going to enter this all at once. So alpha y equals, I've got a big old fraction. Now on the top of the fraction, I have 1.96 because of the 95%, and that's squared. And then I need to multiply it times my p-hat. I'm putting that 0 in there for 80%, but really 0.8 does it. And then q-hat is 1 minus that. All right. And now it has to go over the error squared, but I know that the error cannot be more than 3%. So if you look, I've taken that formula that's right over here and I've put it all in based on the information in my problem. Now this comes out to 682.95. That means I need 683 people in my survey. 683 people in the survey. Because the question was, how many people do you need in the survey? Or 683 adults. Now in part B, it's really the same initial information, but I can no longer assume I have prior information. So if I don't have prior information, I don't have this p-hat. Okay, so the other part that was written up above it applies to both of them. So what I'm going to do is say, okay, well, if I don't have a prior estimate then instead of having p-hat and q-hat, I'll just replace that with 0.25. I'm going to copy that fraction over. But instead of having both of these sets of parentheses, I have 0.025. So I just kind of typed over that. So now I've replaced that. And I get 1,068 because you must go up. Okay, 1,067 is not quite enough. So I need 1,068. So you can see if you don't have a point estimate to start with, you really have to include a lot more people. I mean, that's not twice as much. That's very common. So that's how you can figure out how many people have to be included in a survey. You can get the survey information first and then construct the confidence interval. But before you go to do your research, really that's the point in time that you should just go ahead and decide, well, how confident do I want to be? What am I willing to accept as my error? And then from that point in time, that's how you can actually decide how big your survey needs to be. And one thing you can do with that sort of information is you can say, okay, we surveyed some people, and we're going to take that initial result and get a point estimate. Then with the point estimate, you can calculate how many more people you need to survey so that you could say, okay, now if we want our final results to be 95% confident and no more than 3% off, if I initially surveyed, 200 people, how many more do I have to include? And you could take that initial point estimate and then put that into the formula, and it would save you having to do it with absolutely no point estimate. All right, but that finishes up this lesson. I know this one's kind of lengthy. Please get in touch with me if you have any questions. Thanks.